Good afternoon, everybody. My name's George Smith. I'm a solutions architect at AWS working with financial services companies. And this is FSV303, where I'm going to spend some time discussing with you today options for queryable archives and data lakes on AWS. So during this session, we're going to talk about a pattern for better, cheaper, and faster queryable archives, or we've termed them queryable archive. I've also heard them called active archives. We're going to implement that on AWS, and we're going to talk about why bringing dark data into the light adds value for your enterprise. Here's our agenda. We're going to start with the whys. Why are we in this position? Why are we archiving data? We're going to build one. We're going to demo it, talk about cost benefit, and then dark data and next steps. So why do we archive? This is sort of the story of my life. Prior to joining AWS, I managed database teams and databases for several large financial institutions. And this is how we got to archiving. We started with a transactional system. So we would build a system. In this case, for me, it was a NASDAQ desk or a listed desk or a derivatives trading system. We would start out building these systems, and day one, all we're worried about is getting the transactions through the system as quickly as we can and making sure they perform well and the business is able to execute trades. Day 90 comes along, or day 180 comes along, and now we've got historical database sitting in our day-to-day trading database. And we actually called it that. We called it NASDAQ trading or listed trading. That was the name of the database. At this point, we have a performance problem. For whatever reason, we didn't know at the time what was going on. Things slowed down. So we sat down with the developers. We went through an entire performance tuning exercise and came to the dramatic conclusion that we just have too much data in our database. So we started building archive databases. In this case, we called them history databases. So we had a NASDAQ trading database, and we had a NASDAQ history database. And we would move data on a periodic basis into our historical database so that our trading database can stay small and fast and continue to perform well. This became a cycle. We would do it once a month, once a quarter. However our transaction volume progressed, we would have to archive based on that cycle. Sound familiar to anybody? Is anybody in this audience managing trading system? Was there any transactional-based system where they have to pull data out of their transactional system in order to keep performance stable and fast? Is that a Ferrari shirt? No? What is that, Lannister? Okay. So this is just what we did. This is exactly how we went around creating our initial historical databases. The next thing that happened is regulators decided that we needed to keep data for longer. So we started with the same cycle. The only difference is that our archive databases, we had to keep for 5 years or for 7 years or for some longer period of time. And those databases just grew and grew and grew. And what we had once this happened is a very lopsided environment. We had way more storage attached to the compute than we originally intended. We had designed for holding a couple of terabytes. Now maybe we have 100 terabytes. And then when we need to access these databases, which happened a few times a year, a regulator or a legal event would occur, or something would happen to one of our clients where they would be doing the same thing and they need to access this database. Client would come to us and say, I need this data. We would go out to our archive data store, get the data. If the data set was small enough, it would work fine. If the data set wasn't small enough, meaning I need 5 years worth of trades in IBM or Oracle or Microsoft or something along those lines, performance would degrade. We already have a lopsided environment. We don't have enough compute. Now we have a crisis. We have an end user who needs access to data that can't really get it in a timely fashion. So what we actually did, and we did this, is we searched the environment or our data centers for spare compute. We would build a brand new database on top of that compute, would restore our 5 years or however many years of trades data that we needed, and we'd run the report. The end user was now able to get their data and give it to whomever they needed it. And then we would go back and we would tear everything down. This would take anywhere between 5 and 10 staff days in order to build this up, run the reports, tear everything down again. Not really the best use of resources. And at the end of this, we had an unhappy user. They were not all that satisfied. Yeah, eventually they got their data, but it wasn't the best experience for them. So what if? And we ask ourselves a lot at Amazon, what if? Because we're always trying to figure out what the next thing is, what the new normal is going to look at like. So what if I had an archive data store that was scalable and would perform regardless of the amount of data that I had in there or the amount of data I was accessing? Well, initially I could store as much data as I want and not worry about scaling storage and compute. I can just simply store the data. And I wouldn't be in the fire drill business of building out new environments when my archive data store didn't perform. So no more fire drills. So let's go build it. Now we're going to build this environment in my account in AWS. First I'm going to show you the reference architecture, and then I'm going to show you a demo. And we want to build this without breaking the bank. We certainly don't want to go overboard as we build this. So at 10,000 feet, we start out with all of our historical data sets that are sitting in our data centers today. You think of these as NASDAQ history, listed history, derivatives history. These are all sitting in the data centers when I used to work at the banks and taking up data center space, compute, storage, licensing, and resources. I'm going to extract that data. I'm going to transform that data so that it works with my new storage platform. And then I'm going to load that data into the new storage platform. Once it's loaded, I'll have the ability to explore that data using a variety of tools that exist today within AWS. Our tech stack for this solution, we're going to start with Amazon S3, our simple storage service. This is a secure, meaning you can encrypt data at rest, you can encrypt data in motion, you can control who accesses data, and control who doesn't have access to data. It's a highly scalable, and it is a durable cloud storage platform. S3 stores trillions of objects today and regularly scales to millions of requests per second, and carries 11 nines of durability. We're going to use AWS Database Migration Service, which is a service that we have that allows you to migrate data from point A to point B, and understands several different data sources and targets. We're going to use AWS Glue, which is our managed ETL service. That's a product that allows us to transform the data from the departmental data model, the NASDAQ history or the listed history, into an enterprise data model. So you can look across the enterprise and just say, show me all my equity trades. Or just show me all my trades. We're going to use Redshift and Redshift Spectrum. Redshift is a petabyte scale data warehouse where you can store data locally in the Redshift cluster and be able to access it. And then Redshift Spectrum extends the abilities of Redshift out to S3 and sizes out to exabytes, so you can access a lot of the historical data that's sitting in S3 regardless of size. EMR, which is our managed Hadoop framework, also capable of reading data from S3. And Amazon Athena, which is a serverless query framework that allows you to run SQL statements against data that is sitting in S3. So we're going to come a little bit closer to the ground here and kind of see exactly what we're building. So at 1,000 feet, we have our source database, which is our historical NASDAQ history, listed history database. We're going to extract that data and transform that data using AWS Database Migration Service. And then we're going to store that data into an archive bucket in S3, which is our queryable archive, in a compressed CSV format. Once we've done that, we have solved the query archive problem. We have the data now sitting in a highly scalable and available storage layer that we can run compute against. But we're going to go a little bit further. We're going to then extract that departmental model again. We're going to use AWS Glue to do an ETL extract, transform, load process against that data. And we're going to load it into S3 in our enterprise format. And for the enterprise format, we've chosen, for the data lake, you can see the little lake inside the bucket there, we've chosen Parquet objects because a lot of our customers, we notice as they're building out data lakes, are choosing formats like Parquet. Once the data is available there, in both of those buckets, you can access it and explore it using a variety of services that exist in AWS today. So I have a few demos here where I'm going to take this reference architecture and we're going to go piece by piece and show exactly how this is going to work. So first we have our archive, then we have our data lake, and we're going to talk about step one, which is extracting the data from our historical data stores and putting them into S3. This is DMS. This is the DMS console. I'm doing this with the console. In reality, once this is done, you'd be doing it with batch jobs. But there are tasks and endpoints in the console. A task is a batch job that moves data from point A to point B. You can see I have a source endpoint, which is Oracle, and a target endpoint, which is S3, and that is also displayed in the overview section. I'm going to do a restart. The restart is a full load. It copies the entire table from our source database into S3, and it stores it into a compressed CSV format. The job has been running about 5 minutes, and if we look at the statistics, we can see it's moved about 3.4 million rows. And it's done that right here on the right. We're going to video edit out the boring stuff, come back, 4 hours and 26 minutes later, the job is done, and we copied 167 million rows across. So this data set is a data set that I manufactured to represent orders on a trading desk, orders and executions. At this point, like I said, we have our data in our Queryable archive. So now we're going to want to transform it into the Parquet format of the file, into the enterprise data lake format, which is an enterprise data model, not a departmental model. So there would be, in normal cases when you're doing this, you're going to be validating the data, you're going to be enriching the data, you're going to be pulling in data from other sources so that you can reference the data across the entire enterprise versus just the department, and you're just going to put together a data model that traditionally you might think about as data warehouses or data marts. In this case, we're putting it into a data lake for further processing. We have a glue console. Again, this is going to be a batch job once it's really done. We have databases here. I called the database for the data lake glue catalog. Not a very original name. Within the database, we have tables. There's only one table in here now, and that's the table that we just created with our DMS job in the last demo. This is the CSV version of the orders table. So if we look at our job, we can see a script gets generated by Glue. Glue generates Python, and then you're able to go in there and edit that script if you need to. So we start the job, it's running, and then we're going to edit out the boring stuff. We can see in this case, I think it's running for 28 seconds. And edit away, it's done. It was 2 hours and 55 minutes. We loaded all 167 million rows into our data lake. So now we've got data in 2 locations. The other thing I'm going to show you, and this is going to be a shorter demo, is just loading directly into Redshift. Because Redshift is our petabyte scale data warehouse environment. And you can go with Glue into a variety of sources, Redshift being one of them. In this case, we go right back to the console. Again, this is a batch job when you actually build it. We can see that we added a connection here. This connection is the Redshift Query Archive connection. So now Glue knows about Redshift, and it knows that we want to load data there. So we run our job. We have a CSV to Redshift job. And we do this because if you're running this, you can see this succeeded, and it took 4 hours and 31 minutes. But if you're actually running this in your accounts, you're going to run both of the jobs I just showed back to back in parallel. You don't need to run them. You don't need to run them back to back. You run them in parallel. And that gets your data into your data lake much quicker because you're not waiting on anything. 3 copies of the data. We can access it from any of those copies. And I'm actually going to show you on the query demo accessing it through a few of these services. In this demo, what I'm going to do is start up an EMR cluster. I'm going to access the data in both environments, the archive and the data lake. and then I'm going to shut down the cluster. So let's see how this goes. And this is going to be mostly command line driven. So the first thing I do is execute an API command that starts up the cluster. We can see the cluster starting up, and we can see the cluster ID has been assigned, and that cluster ID ends in GVP. I'm also passing in some configuration information. So for this cluster, I'm telling it to use the Glue catalog as its Hive metastore and as its Spark Hive metastore. And I'm going to tell it not to give me the informational messages, just warning or error messages whenever I run a query. Going into our EMR console, we see there's no clusters running. When I refresh that, we can see the cluster that we just created with that command is now starting. It's been starting for about a minute. This is a 3-node cluster. And we can see the ID matches, and it ends in GVP. We're going to refresh this and edit out the boring stuff. We're 12 minutes later. The cluster's up, it's waiting, it's ready to go. We can see it's the same, it's got a DNS endpoint, and it's the same 3-node cluster. And the ID hasn't changed. It still ends in GVP. So going back, we're going to sign into the master node, just SSH in. We have to answer the SSH challenge because this is the first time we've ever signed into this node because it's brand new. Start up Hive, and we're going to tell it to use the Glue catalog. Showing our tables, we can see we have our 2 tables. I'm going to select count star from the CSV orders table, which is our historical our archive data store. And we can still see we have our 167 million rows that are still in that table. I didn't tune any of these clusters. So these performance is just, the performance that you're seeing here is just out of the box. Now I'm going to read it from the Parquet table, which is our data lake. And we have the same 167 million rows. Now just to verify, it's not just rows that came over. I put together a query that does orders and executions by hour. So this is going to show me how many orders and how many executions were generated and stored in our orders table by hour of the trading day. And in this case, you can see we've got our 7 hours, because I think it's a 6.5-hour trading day. We've got a list of orders and executions. As I said, I generated this data. This is not real trading data. So for those of you who are in the audience who know what trading data looks like, this isn't it. I go back to the console and I terminate the cluster. I do this because I don't need it anymore. The data is sitting in S3. It's alive and well in S3. I only need the compute when I want to process it. One of the big advantages of moving my data into my S3 archive and my S3 data lake is that S3 keeps that data alive. When I used to do this on-premise in the banks, I used to run servers and database software in order to be able to access that data. I don't have to do that here. The data's sitting in S3, it's alive. I only bring the compute to the data when I need to run jobs. Otherwise, I shut down the compute, save that money, save those resources, and the data stays there nice and healthy, waiting until the next time I want to run a query. This is Redshift. Actually, I'm sorry, this is Aqua Data Studio. What I've got open here are some windows that are going to read the Redshift query archive. So the first thing I'm going to show you is, this is essentially how you access data that sits in S3. The schema for S3 is Spectrum. And if you are accessing a table in the Spectrum schema, you're really accessing data in S3. So you can see I've got my Redshift cluster here. I'm creating a table in the Spectrum schema for orders Parquet, which is our data lake. And I have to give it some information about the structure of this data and the location of this data in order for Redshift to actually be able to go out there and access that data. You can see on the left, I've highlighted a public schema. That is the local data. So we're going to compare the two. So here I'm going to select count star from the local data set, because it's public. 167 million rows, less than a second to execute that query. Now I'm going to do the exact same query as orders and executions by hour against the local data set. This query ran in 4 seconds and gave me the same results that we saw before. So you can see I'm using 2 services so far, and I'm able to get the exact same results from this. Same thing from the data in S3. I'm going to get the same results. It's going to run a little longer because it's going through Spectrum, not local data. 167 million rows, 3 seconds. And then orders and executions by hour. Pulling that data out of S3 using Spectrum, the data comes back in about 5 seconds with the exact same results. We showed the EMR cluster and the Redshift cluster, and just like the batch jobs, you could run these both at the same time. You can have multiple compute sources accessing your data in your data lake or your archive at the exact same time. This is bringing compute to the data, and I can bring multiple compute stacks to the same data and access that data at the exact same time. And S3 will serve that data to each source. The last one I'm going to show you is Athena. Athena is unique in that it's a serverless infrastructure. I'm not starting anything, I'm not running anything, I'm just going to the service. So I'm going against the Glue catalog, we've got our same 2 tables. We look at the properties of the Parquet table. It's got the same structure, it's the same location as the data set we've been accessing all along. And I'm going to run the same 2 queries. Since Athena is a managed service, somebody else is managing the cluster's performance and availability. So here, I got my 167 in 1.43 seconds, scanning 0 kilobytes. Now I'm going to run the orders and executions by hour. This query, I think, runs in 1.89 seconds or something along those lines, and scans 85.35 megabytes, but gets the same results. The megabytes are important to Athena. They're also important to Spectrum, because for both of those services, you pay by query, and you pay per terabyte scanned. So it's $5 per terabyte to run to scan data in either of those services. So this query, which scanned 85.35 megabytes, I calculated this cost 0.00043 cents. So this is a very good platform, as well as Spectrum, for doing maybe some ad hoc queries, or if you're looking to go back in time and look at data that's a bit older than what you would consider current historical data. All right, we'll talk about that in a minute. So when I was, again, working in the banks, I knew I had an archive data problem. I knew it was a pain in the neck to go and get my archive data, and it wasn't really usable. And I knew that there was a better way to do this. The problem is that I could not cost justify to my management going out and building this environment. And right now, what I'm going to do in the next couple of sections is try to cost justify to you why this solution is going to end up costing you less money than your current solution, which is what I described from my history, and give you better access to your data and provide better ability to analyze that data and produce value for your organization. First is you have a single golden source of truth. Instead of going out and replicate, we have our archive and our data lake here, going back to, oh, I did this wrong. So going back to what we're talking about our archive and our data lakes. We have a single golden source of truth. One copy of the data, as far as I'm concerned, sitting in S3. S3 really has multiple copies, highly available across the region, but I'm paying for one copy. When I did this on-premise, I had a primary database, entire stack. I had a secondary database in order to be able to have high availability and disaster recovery, so in case anything happened to one data center or one environment, I would build it in the other environment. And I had backup copies of the data. In this case, we're keeping the data in S3, single copy of the data. The other thing I had on-premise is I had several data warehouses or several data marts that would do end-of-day processing. So when my trading day was done, I would send the final batch cut to, call it 5 systems. It was really more than that. They would all load that data on independent systems and start processing. In this model where we bring the compute to the data, not send the data to the compute like I did before, I load this data into my data lake, one system, and I start up 5 compute stacks, and I process the data. That's what single golden source of truth means in this context. The next is right-sizing compute for workload. So for this, we're really talking about the compute that we bring to the data. So I just mentioned I start up 5 compute clusters to process my data for the overnight batch. But what happens if a Brexit occurred? I mean, I worked in trading environments and trading houses, whenever a Brexit occurred, or an election surprise occurred, or a tweet went out, or say it was Cyber Monday, volumes would go through the roof. And we would have to run around the environment checking all of our infrastructure, making sure we can handle that night, that trading volume, and that night's overnight batch within the windows that we had. I mean, I don't know how many people, I think there's a few people over here running trading desk. I'm sure you're doing the same thing if anything happens like that. In this model, say I'm running a 10-node Redshift cluster, and that's my normal volume Redshift cluster, or a 10-node EMR cluster for normal volumes. Brexit happens, or an election surprise happens, volumes go through the roof. I can start up a 30-node cluster today. I don't need to start up another 10-node cluster. I just start up a 30-node cluster. As long as my application is designed for it, it'll scale out to 30 nodes and process the overnight workload. 2 weeks from now, 3 weeks from now, when volume has calmed down, I can go back to a 10-node cluster. I don't need to provision my infrastructure for peak anymore. I can provision my infrastructure for what I need when I need it. And that's a big advantage, I think, in this model. And the next is availability. I mentioned earlier that I used to run 2 stacks, a primary stack and a DR stack. And this is really talking about the compute at this point. In data warehousing environments, it was very difficult to run 2 stacks. I can certainly purchase both stacks, but if I had 100 terabytes or 200 terabytes of data, it was really hard to keep everything in sync. It was a lot of heavy lifting and a lot of moving parts. Right? And I'm paying for everything. In AWS, we build our environments out in regions, and we build out availability zones within those regions. So a region is a geographic location, US East 1. That's in Northern Virginia. An availability zone is a place where we build data centers, 1 or more data centers per availability zone. And those availability zones are separated. They're on separate power grids. They're in separate floodplains. And they're typically separated by miles and miles of distance. So if anything were to happen in one availability zone, it wouldn't impact the other availability zones. So as you're running your compute in AWS, you start up compute in your availability zone. S3 is a regional service, so S3 is available in all availability zones in the region. If one availability zone goes away, S3 doesn't go away. S3 will be available for the entire region. If something happens to either the availability zone or your compute in that AZ, you select another availability zone. You would have done this beforehand. You start your compute, you move your compute into that other availability zone, and you continue processing. This simplifies, at least compared to what I used to do, and we were pretty good at it in the banks I've worked at, but this simplifies compared to that exactly how you would build and manage your disaster recovery or high availability environments. Okay. Now we don't want to break the bank. We said that at the beginning. So we're going to talk about some of the efficiencies that you gain that will ultimately net you dollars. So the first is storage efficiencies. When you're storing data, you pay for what storage you need to store that data, whether you store it on-premise or whether you store it on AWS. The difference is that on-premise, you're paying for way more than just the initial copy of the data, and you may not have the same compression options available. I ran databases for many years, Sybase, DB2, Oracle, SQL Server, Teradata, all of them. They all have compression options, but I typically would get 30% compression, 40% compression whenever I was able to compress my data. Looking at the data that we used in the demo today, in Oracle, that data was about 76 gigabytes. The actual data, because I extracted it and put it into a CSV file, which is a text file in an uncompressed format, was 56 gigabytes. So there was 20 gigabytes of overhead. Some of that was inefficiency in the way I put it out there. I know if I would have done a reorg, I probably would have gained some of that back. So, you could just say instead of it being 76, maybe it's 66 or something along those lines when you actually store it and you're making sure that the data is organized correctly. Putting it into Redshift in a columnar format, it's only 17 gigabytes. But when you get it into S3, in your archive data store in your data lake, it's 5.5 and 4.5 gigabytes. So for the price of I'm sorry, 5.5 and 3.5, I apologize. For the price of about 9 gigabytes, I have a historical archive and I have data sitting in a data lake versus my 76 gigabytes for the data sitting in Oracle. So I'm going to save in my storage cost. And your mileage is going to vary because some of your data sets are going to compress better than others, and you might have various compression options on your databases, but either way, I'm betting that you're going to save on your storage cost. Additionally, there are compute efficiencies. Again, I mentioned that S3 keeps the data alive for you. With Oracle, a SQL Server, Sybase, or DB2, or Teradata, or any of those other products I've worked with, I needed to run servers and storage in order to be able to access my data. So in order to keep my historical data sets alive, I had to run 24/7 servers and storage and database licensing and OS licensing, et cetera, plus maintain all those environments, power all those environments, cool all those environments, just so that my data would stay accessible. By putting it into S3, I don't have to do that. And you can see the price varies dramatically. I'll point out that the Oracle price, you've got two prices there. One of them is a bring your own license price, and the other is if you pay for the licensing with your AWS bill. But for 21 cents, I was able to put this data set, 21 cents per month, I'm able to put this data into S3. And granted, this is a very small amount of data, and we're talking about standard S3 here. So if we look at a petabyte of data, these are today's prices. If I put this petabyte of data into S3, standard tier S3, which is what I've been doing this entire presentation, it's $22,583. Now this petabyte might represent 5 petabytes of data that's sitting on premise today in my historical archives just because of the compression that I'm getting. But this is historical data. I don't need it to be as accessible as current data. So I can use lifecycle policies and I can move along these tiers of services and I can move the data from standard S3 for maybe the current year's worth of data. Then I can move it into S3 infrequent access for anything greater than a year. And then I can move it into Amazon Glacier for maybe anything greater than 3 years. And I can build, with S3 and S3 infrequent access, that's pretty straightforward to do with lifecycle policies. And the data is still accessible, so you don't have to do anything special. But with Glacier, you're moving it into a cold storage environment. So if you want to access that data, you have to basically go out and request that data be recovered and put back in S3 for you. And you could build a system that will go out, pull the data out of Glacier, put it into S3 so you can start up some compute, run your reports, and then shut down the compute and then delete that data. Pretty straightforward thing to do. And with Glacier, you can get that data back in 5 minutes or 12 hours, depending on how you want to design your system, what you want your SLAs to be, and how you want to manage your budget. So you have the ability to do something that we've always wanted to do, which is to move colder data onto cheaper storage platforms, which is a little bit harder to do unless you've got a system to do this for you on premise than you can here where it's all built into lifecycle policies and the like. So you can also save even more money by selecting the right storage tier for the age of your data. So let's talk a second about dark data. I'll let you guys read this while I get a drink, because I know you're all reading it. What this article actually discusses, and spends a lot of time discussing, is accessing data that is unstructured. But there is a section of this article which talks about structured data that is not accessible. And that structured data that's not accessible is the data that's sitting in my historical data stores. And in some cases, in my data warehouses and data marts. And the reason it's not as widely as accessible, we know why it doesn't work for the historical data stores because they're lopsided. There's way more storage than compute. Whenever you try to run any analytics against it, it just falls over. And then we have to go out and build brand new environments just to be able to run certain queries. But once we bring that data into the light, and once we make that data accessible to a larger part of the organization, without seeing the performance issues that we're seeing in the archive stores that I've worked in, a lot of interesting things start to happen. You start to be able to run analytics against that data store. Your data scientists can go nuts and actually access years more data than they probably have today and be able to run the reporting and analytics that creates insight for your organization and unlocks value and helps you deliver to your customers the things that they want when they want it and makes your organization a lot more efficient. So going back to our architecture here, we've now illuminated our 2 data stores. We've illuminated our archive data sets, and we've further illuminated a data lake because the scale at which we can start compute against both of those data sets has increased dramatically. Which leads us to what we call a flywheel for data. So we start out with sources of data. Through this entire presentation, I've been talking about user activity and purchasing. Customers entering orders, those orders getting executed, and them end up purchasing securities. The data now is in a platform that allows for better analytics. Those analytics allow for better decisions, and we're able to create better products and services for our customers. Our customers are a lot happier. We're a lot happier. We're doing things a lot more efficiently. Other users in our organization are going to notice this. So they want in at this point. So they're going to bring in more data to the data lake. That data describes more and more about what our organization does on a day-to-day basis and how we interact with our customers. The analytics available now to this data open up dramatically because it's basically all of the analytics and reporting services that exist within AWS today. So they're able to run more reports and gain more insight than they can right now because all these services exist. We also have artificial intelligence, deep learning, neural networks, machine learning services that we keep developing and keep adding to. So that is going to continue to produce better decisions, better products, which attracts more users, and this cycle just keeps continuing. So it starts to feed on itself, and we end up finding ourselves in a much better place with more opportunity for analytics and for storage. Analytics and reporting. What can we do next? I mean, this is day 1 of reInvent. So let's talk about what we expected. These are the topics we thought we were going to discuss at the beginning of this session. We've gone through all of these topics, and we've discussed them in detail. So what can you do now? Well, you've got a week of reInvent to go to. There's a lot of exciting things going on here, and you're going to learn a lot of really new, cool things that we're doing and what you can be doing. You're going to hear from other customers. So for the next week, you're going to be spending it with us, just filling yourself up with knowledge and looking at all the cool stuff that's going on. Well, when you get back to work, just go and look at your archive data stores. Most of you have them. Just find out what they cost. What does it cost you to store all that historical data? Just look at your department. Maybe look at a couple of departments if some of you run multiple departments. And then look at what it would cost if you do what we just discussed. If you took that data, you moved it from your on-premise database servers, you put it into S3 and decommissioned all of the on-premise work and continue to do your processing from here. We have a calculator. We call it Simple Monthly Calculator. This is the link, but if you go into a search engine and type in AWS Simple Monthly Calculator, this link will come up, and you'll be able to use it to determine what it costs per month to do your historical data sets in AWS. At that point, you can ask yourself whether or not this is going to save your company money or not. Whether or not this is something that you can sell to your management because there really is a value proposition here. And once you've convinced yourself of that, go build it. Doing a proof of concept on AWS is very straightforward. You pay for what you use, and if you're not using it, you don't pay for it. So you can put some data out there, run some compute against it, prove it all works, and then shut everything down. It's only going to cost you what it would cost to run that for the short period of time of the POC. And we have people here at AWS that would love to help you guys do that. So at this point, I'd like to thank everybody for spending the time with me today. I will be up here for a bit more to answer any questions. There's also surveys that you guys can fill out if you could to talk about this session and what you thought about it. We want to make sure that we're providing the right kind of content and the right kind of topics to you going forward. Thank you very much.